Okay, good morning. There is one part of this chapter which is left. If you remember, I skipped that one, so I am coming back to it now, and that's the application of the chain rule. That's actually an important lesson. Uh, Let me try to start motivating you by what do I mean here. So assume that you have a function. So do you remember what was the chain rule? The chain rule was that if I have f of g of x, and then I am interested to take the derivative of that, this becomes what? F prime of g of x multiplied by g prime of x. So that was the content of the chain rule. What is the meaning of this derivative here? Because there is only one variable that you see here, definitely this prime means derivative with respect to the x coordinate. Yes? Okay. But I told you that, for example, you can consider this to be u. If I say that u is g of x, then how should I read this? Then it becomes f prime of u, f of u totally prime. Be careful about not missing these things. And then it becomes f prime of u multiplied by u prime. So that is the compact version of what we call the chain rule. But remember, u itself is a function of x. Okay. Let me tell you something like this now. Forget about this momentarily. If I write f of u, u is the name of my variable, to be, for example, u squared, then if I ask you to calculate f prime of u, what do I mean actually here? What is the answer to this?
2u.
2u, okay? Because when I write something like this, you interpret u as your variable, and when you take the derivative, it's exactly similar to x. And then when I say prime, what do I mean? I mean the derivative with respect to the variable that you see in front of your eyes, so the answer is that. Okay, but let us assume that u itself is also a function of x. For example, u itself is, let us say, x to the power of 3 plus 2x. Okay. So in principle, this u itself is a function of x. Instead of that, I can say u depends on x according to this relation. And now if I ask you calculate u prime of x, what do you answer? What is the answer to this now? It's 3x squared plus 2, yes? But there is no matter of confusion. You see, I am using the same symbol prime here, and the same symbol prime here. But you understand here, prime means differentiation, yes? 2, yes, thank you. So this prime means what? Derivative with respect to u, but this prime means the derivative with respect to x. Yeah, so it is not ambiguous here. But now think in this way. F is a function of u according to this relation. U itself is a function of x according to this relation. In other words, when I say f is a function of u, what do I mean? It means that when I start changing u, f will change. When I say u is a function of x, what do I mean? It means when I change x, u will change. Now, can you say that if both of them are happening at the same time, can you say that f can also be viewed as a function of x? What does this sentence mean? It means that if I change x, do you expect that f changes? Yes or no? Definitely yes, because if I change x, u changes, and when u changes, f will change. So I would say that if f is a function of u, u itself is a function of x, then it means that if you want to, you can interpret f as a function of x as well. Okay? So in that case, if I want to take the derivative of f with respect to x, then I am not allowed to use the same symbol because then it is ambiguous. I have two variables u and x, then I have to mention that which variable I mean with respect to which one. So in that case, if I write d dx of f, then it is clear. So the Leibniz notation here is better, because when I write this, I mean the derivative of f with respect to x. When I write df du, I mean the derivative of f with respect to u. Okay, there is no ambiguity. If you have more than variable, the Leibniz notation is superior to this prime notation. Yes? Okay. If I ask you on the board, if I ask you what is this, which one of these things that you see on the board is the answer to this? Which one? Can you tell me what should I write instead of everything you see? What should I write below this?
F prime of u equals
2u. This is 2u. Yes? And then if I ask you this one, what should I do? There are two ways we learned before. One is to find the connection between f and x and then take the derivative of f with respect to x. The second method is to use the chain rule. Okay? So if I ask you what this one is, method number one is, because you see I want to find the derivative of f with respect to x. I do not have it directly in front of me because the connection between an f and u is direct. Yes? So I have to find the connection between f and x first. Okay, so what should I do? I would say that f is equal to u squared, but u itself is this quantity. So then it becomes x to the power of 3 plus 2x to the power of 2. Yes? This is the relation that express f in terms of x. Is that clear? Okay, now if I ask you what is this one, then you should be able to answer in principle. What is the answer to this? Take the derivative of f with respect to x. What happens? What's the answer, by the way? You should be very good in calculating these derivatives. What's the answer? So how is that possible? You cannot take the derivative of this function? You cannot differentiate it?
Which one?
This one, this one.
2 of x3 plus 2x.
No. Not complete. Times the derivative of the base, which is 3x squared plus 2. Yes? So this is the way that you do it. One way of doing it. So the derivative of f with respect to x is equal to this quantity, which is what? Is u prime, which is the derivative of u with respect to x. Do you see? 3x squared plus 2 is exactly u prime. But what is u prime? It means the derivative of u with respect to its variable x multiplied by, what is this quantity? It is derivative of f with respect to u. Yes? Because the derivative of f with respect to u, you told me it is 2u, u itself is this guy, so 2u becomes exactly this. So it's a very easy way to understand things. Don't get confused. It seems that they are fractions and we can simplify them. So this is why it is good to, it's a very good way of remembering things. So let me just tell you what I did. So f is related to u is related to x. It means f is also related to x. F in more correct way, I say that f is a function of u. It means when I change u, f changes. U itself is a function of x, meaning that when I change x, u changes. So it is very clear that when I change x, f will also change, because changing x will give a change in u, and the change in u will give a change in f. Okay, now the point is that if I want to calculate the derivative of this one with respect to this, I want to measure how the change in x will affect the y. What will affect y? I want to see how f changes if I start changing x. This is the meaning of df dx, the derivative of f with respect to x. This tells you that to answer this question, because this connection is not direct, you can do it like this. You can take the derivative of f with respect to the intermediate variable u, but the condition is that you have to multiply by the derivative of this intermediate variable with respect to the final variable. Yes. Memorizing this form. This, by the way, that's exactly the chain rule. Yes. That's exactly the chain rule. Because, do you remember, this is the chain rule. You see, f is a function of u, u is a function of x. If I want to take the derivative, I take the derivative with respect to u and then multiply it by the derivative of u. Okay? This is exactly the same formula that I have written here, but that is a better way of writing this in this new context, yes? Is that clear? Okay. So let us see how this is actually working in some practical problems. I think I will start with an example here to be able to solve. These kinds of problems you need to know very well, of course. These are a little bit hard because these are word problems and you have to use the chain rule to answer these questions. So let me write this question. Air is being pumped into a spherical balloon at the constant rate I don't know, say 10 centimeters, 10 cubic centimeters per second. The question is, how fast is the radius of the balloon is increasing at the moment when the volume of the balloon reaches 36 pi cubic centimeter. So air is being pumped into a spherical balloon. So I'm modeling my balloon. Of course, the ideal balloon is not a sphere, but it's a very good model, I think, at least for the first approximation. So what I am doing, I am pumping air to my balloon with a constant rate, okay? The rate is 10 cubic centimeters per second. So if you wait 1 second, 10 cubic centimeters of air has been pumped into the balloon, yes? For example, if the volume of the balloon is 0 initially, 1 second later, it contains 10 cubic centimeters of air, and if you wait 2 seconds, because the rate is mentioned to be constant, if you wait 2 seconds, after 2 seconds, what will happen? We will have 20 cubic centimeters. Okay, And the question is that how fast is the radius of the balloon is increasing at the moment when the volume of the balloon reaches 36 pi cubic centimeters. So when you are increasing the radius of the balloon, the volume of the balloon, at some point it reaches to this value, the volume becomes this, and still we are pumping air into it, so it will start increasing. We want to see what is the rate at which the radius increasing at that particular moment. Yes? Because my intuition is that in the beginning, what happens, that in the beginning the radius increases faster. And then when the balloon becomes bigger, the rate at which the radius is increasing, of course the rate at which the volume is increasing is constant. Yes? But do you feel that? I don't intuitively it seems that when the balloon becomes bigger, the rate at which the radius is increasing becomes slower. Okay, so the question is that we want to solve that problem. Okay, how do we solve the problem here? So we have some quantities that you see. Let me call it volume, V for volume, it's good, and R for the radius. These are the quantities involved. But by reading this question, there is also another quantity involved. What that quantity is?
Time.
Time, exactly. Because first of all, you see this second here, so time is somehow involved. Another thing is that when in English, when you say how fast, it means that you are talking about the rate of change of a quantity with respect to time. For example, when you say how fast the particle is moving, of course you're asking about the speed. But what is a speed? Speed is the rate at which the particle's position is changing over time. Yes? Okay, so you know that. So there's another one which I call time. Whenever this happens, you have this scenario, you know, V or T, you are interested in the derivatives with respect to time. Because when you are asking how fast the radius is changing, it means that you want to calculate the rate at which the radius is changing over time. Okay? Okay, so one thing that is definitely helpful is the formula that relates these two quantities. So you can check it in the formula sheet if you don't have it in your memory, how the volume of the sphere is connected to the radius of the sphere. Well, how that is, it is a famous formula of V is equal to 4 over 3 pi r cubed. So, but is this a correct picture I draw here? V is directly a function of r. But r itself in our problem is also a function of time. Is that clear? V depends on r. R itself depends on time because by passage of time, the volume is the radius is increasing and then the volume is also increasing. Okay, but the question is that I want to calculate the rate at which the radius is changing. So what I am interested in is dr dt. Yes? This is the question. How fast is the radius of the balloon is increasing? This is the question. Yes? Okay. So what do I have? I have one formula that dv, the rate at which the volume is changing over time, is equal to the rate at which the volume is changing with respect to the intermediate variable r multiplied by, can you complete it? D capital R over dt. It's very easy to memorize that because it seems like a fraction. You cancel them, you get this back. Yes?
Although I have a question, how you came up to the reasoning that V should be first and not R?
That's a good question. You can do it the other way around.
Is it possible?
Yeah, it is possible. But then the reason that I did it, by the way, it's a very deep and good question. I was just also thinking about that. Okay? Because you might say that this is more natural to start from R because R is the target quantity. The reason that I didn't do that because in that case I have to write R in terms of V. Yes, so I have to do some algebra here. Yes, so because of that I didn't do this. But if you do this, so it means that it becomes 3v over 4 pi cubic root. This becomes r. So the functional form becomes more involved. Yes? So, and then it doesn't matter at the end. Only I am making life harder for myself. And that's good. That's a good question, by the way. So what should I do now? So what is he asking you? So it means that he is interpreting r as a function of v and then v as a function of t. In this problem, this is more reasonable to start with. Yes. In that case, can you write this? You can write dr dt because you see that the question mark is dr dt, so it is natural to start from this perspective. And then what should I write then? Can you tell me now? Yes. dr dv, yes. And then dv dt, yes? Okay, and then you see that here I have to take the derivative of r with respect to v. So I need to do this algebra to find r in terms of v in order to be able to calculate this. And then I hope that you agree with me, it's a little bit harder. If I ask you what is dr dv, then what you need to do, you need to interpret it as the third root of this, which is a constant, but multiplied by v to the power of 1/3, and then r. And if I ask you to take the derivative of r with respect to v, then this is a constant, and then 1/3 goes down, v to the power of 1/3 minus 1, which is minus 2/3. You see the calculation is more involved. But that is a very good question. And I hope that you understand that if you write it in that way, that's also correct. You can see that this will work. But let us go back to this picture. Let me finalize that. If you have questions, I come back to it. Go to the problem. V is a function of r is a function of t. So if I ask you, how can I calculate the derivative of v with respect to time, you will tell me you can calculate it using the derivative of v with respect to r, but you need to remember to multiply by the derivative of r with respect to t. Yes? Okay. But now, can I calculate this? Yes, I can calculate it much easier than I could calculate this, because this is a polynomial function. Yes? So can you tell me what is dv dr? What is dv dr? I want to take the derivative of v if r is my variable. 4 pi and 3 are constants. So what should I write? I should write 4 pi over 3. I don't care. And I take the derivative of r cubed, which is easier. What is the answer?
3r squared.
3r squared. And this 3 and that 3 are cancelled, so I get 4 pi r squared. So this is 4 pi r squared. So if you don't mind, let me put everything back. So dv dt is equal to 4 pi r squared dr dt. This is what I get. Yes, but now let us go back to the problem and put the numbers in. So I want you to tell me which numbers is suitable for which one of them. This one, of course, I do not have any numbers because that's exactly my question mark. So this is my question mark. But can you tell me, according to the problem, read the problem again. What can I put here? This is the rate at which the volume is changing over time. Can you read the problem and tell me which number plays the role of dv dt here? Yes? 10. And that rate is constant. So, of course, it depends at which time I am looking at the problem, but this does not depend on time according to the problem, because the rate at which the volume is changing is constant, and it is always 10. So this one I put 10. Okay, now the point is that 4 pi, this is my question for you. So this question mark, I will write it down here. But this r, which r should I put here? Because the volume is also changing. Is that on? This is important, by the way, because you cannot say that R is constant. R is changing over time. Which one of those R's, according to the problem, I have to put here for R? I just want everyone thinks about the question. This one, I don't care about which time I am looking at dv dt, because according to the problem, that's constant. Okay? But here, which R I should put here? Yes, Hussein?
I'm expecting 36 pi.
No, be careful, that is not radius. 36 pi cubic centimeters, when the volume of the balloon reaches to that. Yes?
36
Or
pi.
when the volume is that number.
How should I calculate that? So this is my duty to calculate that particular R.
So you put 36 pi into the volume formula.
Exactly. So this means that I have to, when I reach to this point, I have to actually step behind a little bit and then put this equal to that volume to see at that time that the volume reaches to this, how much is R. Okay? So what is that R? This is simple to calculate. This pi and that pi are gone. This 4 and this 36 are simplified. So it is 9. I multiply by 3. So R cubed is equal to 27. So this is, what is R then? Is 3 centimeters. So, but I want you to understand this R is not a constant because R is changing, but at the moment when the volume is this value, at that particular moment, only for just one single instant of time, the radius is this value. And that is the value that I have to plug here. Yes? So this becomes 3 to power 2. This is the most important part of the problem. Do you understand what's going on? Yes? Okay. And then what is left? The only thing left for me is this question mark. So just do the calculations a little bit. So 10 is equal to 36 pi. Is it a coincidence? Yeah, I don't know. This is the same thing. Yes, 36 pi. So your answer was coincidentally correct here. Yes? And the final answer is this one, times dr dt. But then I want to find dr dt. What is the answer? It's 10 over 36 pi, which I simplify to 5 over 18 pi. But if you write like that, it is not complete. Why? If you write dr dt is 5 over 18 pi, what is that? Whenever you want to write a problem in physics, you have to write the units. So what is the units? What are the units here? dr dt. R is a length. What is the length measured in this problem? Centimeters, and time is measured in seconds. By the way, you have to be careful. If the units are not consistent, you have to decide to convert all the units into one single type of units. Might be, I don't know. Might be in this problem I have given you cubic meters per second, and in this part I have written 36 pi cubic centimeters. You have to be consistent in the units to use. Yes?
Should the answer be in centimeter per second?
Centimeters per second. So this is a have to, by the way. One part of the points is related to writing the units. So what happens? dr dt is equal to 5 over 18 pi centimeters per second. But to be really rigorous, if I write this, the interpretation is that the rate of R is constant. But I want you to understand that the correct thing to write is T node here. And then what T node is that instant at which the volume is 36 pi cubic centimeters. But usually we don't write this, but I want you to understand that. If I change that instant of time, this rate might change. Okay, Now let me ask you one question. Before I solve the problem for you, hopefully this is your intuition, that when the balloon starts becoming bigger and bigger, the rate at which the radius is increasing becomes smaller. Yes? Is that right? How can you prove this using this? How can you mathematically prove that your intuition is true? This will not help because this just gives you the rate at which the radius is changing at one instant of time. I want you to show me why your intuition about the rate of increase of the radius is true. How can I show that? You can come back to this general formula. So this tells you that dv dt is always like this, regardless at which time you are looking at it. Yes? But now, let me write this at some instant of time, yes? At some instant of time. Let me write this more explicitly. If I write it more explicitly, it becomes this. R is a function of time, and then dr dt at that time, yes? This is the expanded version of this formula. Yeah, so we just usually suppress writing that t. But then, let us check this value. So dr dt at some point t is equal to the left-hand side divided by this. Yes? But this is, according to our problem, is always the same number because that's a rate of 10. Yes? So then what happens? It becomes, and this I simplify, it becomes 5 over 2 pi multiplied by 1 over r squared, this one. So then I hope that you understand what is happening. This is the rate at which the radius is changing, is equal to a constant multiplied by 1 over the radius squared. So what happens? When the radius becomes bigger, this number becomes smaller. And it means the rate at which the radius is changing becomes smaller. So it is clear by the passage of time, because the radius increases, the rate of which the radius is increasing slows down, yes? Is that clear? Okay, so that intuition was correct. So that's one problem. Let me give you another problem, okay? So if I want to give you another problem, let me just start, yes, doing this. So consider that you have a rectangle. You have some rectangle. You have one particular height, one particular length, and from that moment, you start increasing the length and simultaneously decreasing the height. This will affect, of course, the area of this rectangle. We want to understand this a little bit. So I'm lazy to write everything, but let me just talk about this orally. So I would say that, assume that the length increases at the constant rate of, for example, 2 centimeters per second. So I have one given rectangle, and then I start actually increasing the length at a constant rate of 2 centimeters per second. And simultaneously, and the height decreases at the constant rate of 1 centimeters So let me write it 3 centimeters per second. So what does it mean? It means that if I start with a given rectangle, 1 second later, the length is 2 centimeters longer, and simultaneously the height is 3 centimeters shorter. That's what I am doing. Okay? Now we want to understand, so answer this question. How fast is the area changing at that moment when the length is, say, 20 centimeters and the height is 10 centimeters. So I don't know anything about the initial values of the length and the height, but assume that they are in a way that this is consistent with this data, yes? Okay, we want to answer this question. So how should I solve that problem? So you want to say something about the rate at which the area is changing. So you need to have a formula so that connects the area to this information given in the problem, meaning the length and the height. And that's very simple. Yeah. So the area, for good reason, I can call it A. And then this is, for example, length multiplied by the height. This is the area. Okay, can you tell me, read this text, what is my target? What should I, a mathematical symbol, what is wanted in the problem? How fast, again, means the rate with respect to time, yes? So this means that what is wanted? If I want to write something in mathematical language, d capital A dt is wanted. To be honest, this is not the exact story. The exact story is I should write t note, something there. Because I am not interested in the rate at which the area is changing at all possible times. I am interested at that moment when I have these informations, okay? But this is always implicit, so I don't need to write it down. This is wanted. So I want to take the derivative of this one. Let us see. A is a function of two variables, apparently. Not apparently, really. A depends on length and height. Okay, but L itself depends on time. H itself also depends on time. Yeah, so if you want to have a diagram, it's like this. A depends on two quantities, but L depends on T, H also depends on T. So it means that finally A is really a function of time. Yes? So this is meaningful to ask. Okay? So what we do here, I take the derivative of A with respect to time. Be careful about that. So I have to take the derivative of the right-hand side with respect to T as well. Okay, but can you tell me, this is probably not that much related to the chain rule, but that's also good to understand about this. So how can I proceed? Can you help me to do that? Remember, L is a function of time. H is also a function of time. I have multiplied them and I want to take the derivative. Which rule is that? It's not the chain rule, but it is which rule? Two quantities depending on the same parameter t. I multiply them and then I want to take the derivative. What rule is that? What did you say? Pardon?
Distributing though?
No,
Factorizing?
no, in derivatives.
Oh.
The product rule.
Oh yeah.
Yes? Because you so exactly, do you remember we talked about this? If I give you a function x, I give you another function e to the power of x. If I multiply them, and if I ask you to take the derivative of that one, that is the product rule, yes? But here, t is playing the role of my variable, yes? So how can do you remember the formula? The formula of fg prime. What was it?
F prime G.
F prime g plus fg prime.
Yeah.
And that's exactly the formula. So that's the formula that I have to use here. So this becomes the derivative of the first one multiplied by the second one itself plus the first one itself multiplied by the derivative of the second one. So what I am using the product rule. Is that understandable? Okay. So now everything is in order. So just read the problem once more and to put the numbers in. This is my question mark. Okay. So the question mark is dA dt is equal to. So can you tell me what is dL dt by reading the question? The length increases at the constant rate of 2 centimeters per second. So dL dt is 2. But what is h? Again, the same story. H depends at which instant of time you are looking at it. But it is given at which instant of time? Oh, I haven't given you that information. Yes, I have given you. When the length is 20 centimeters and the height is 10 centimeters. So the height, I put 20. Not because the height is always 20, because I am interested in the height at that moment. Okay, plus, yes? Pardon? This is, what? It's 10 centimeters, yes, thank you. This is 10. And the height is 10 centimeters, thanks. Plus, what is L? 20. But this is, I want to hear from you. What is dH dt? Don't
Minus.
spoil the problem. Yes, minus. You have to put the minus. Because I have mentioned that the height decreases at that rate. Yes? So this means that you have to understand that you have to put minus 3 here. And then you do the calculation. So it becomes 20 minus 60. The answer becomes minus 40. Okay? But you have to apply the units here as well. What are the units? This is also important. This question mark is the answer to this. Area over time. Yes?
Centimeters squared per second.
Yes. Because how did you understand in centimeters? Because you see that everything is expressed in centimeters, so centimeters squared per second. What is the meaning of this negative sign in my calculation? Is it wrong or what is, yes?
It decreases.
Yes, so it means that the area is actually decreasing over time, and it is reasonable, yes? Because length and height have the same kind of effect in the area, on the area, and of course I am increasing one of them and decreasing the other one, but the rate of decreasing is faster. So it is clear that the area is not growing, actually, it's actually becoming smaller. Is that clear? Okay. So I wouldn't say this is an application of the chain rule because I didn't use the chain rule. I used the product rule, but that's also good to know. Another problem, let me just make it a little bit harder. I have seen some of these, by the way, in the national exam, so if I remember correctly. This is an interesting problem. Let us try to solve it together. So I don't know how to state it. So let us, I don't know, assume that I have a laser pen. I don't know. This is, for example, this is my line. Okay, and then I have my laser pen here. So assume that the height is 1 meter here. Okay, and then I put my laser pen here, and then I have the light point here. And then I start rotating my pen This point will go here, then I rotate this, this will go here, yes? So this, I want to answer this question. If I give you the angular speed of my rotation, what will be the speed of this moving point light? Light point, yes? Is that clear? This is a sensible question, because if I have my pen in this direction, this point will be highlighted. When I start rotating it, for example, in this direction, then this point will be highlighted. It is clear that when I start rotating, other points will be highlighted. So it seems that this point, it doesn't seem exactly that it will do this. This point is moving here. Yes? And there is a speed for that movement. I want to connect the rate at, I want to connect the angular speed of my rotation with the linear speed of this light point. Is the question clear? Yes? So we want to connect these two. The problem is definitely clear, because I can take my pen, I can just shine it here and just rotate it. You will see that this point will move. Okay? And it is clear that when I do it very slow, that will also move a little bit slower. When I do it faster, it will go very fast. But I want you to understand what is the connection between this rotation and that speed. Is that clear? So let us solve the problem. How do you solve it? To be clear, I give you omega. What is omega? The angular speed. For example, omega is good to say 1 radians per second. It's reasonable. Probably I can do it by hand, yes? What is 1 radian approximately in degrees? Do you remember?
57.
57. So it means it is reasonable. In 1 second, I really can move it 57 degrees, yes? It's not that unreasonable. So that is a reasonable speed, and that's not fast, by the way. So let us assume that this is 1 radian per second. And then my question is that, what is the speed of this point light? Light point, which one is correct? Light point, yes? Pardon? Light point, yes? Or point light? Forget about that. What is the, I think point light should be correct. Light point? Okay, light point. Okay, light point. So what is the speed of light point? That's my question. We want to answer that question. I give you this height, 1 meter. I give you this angular speed of my rotation, and I want you to calculate this speed. Of course, it is clear that I should go up, then I will actually, I don't want to do that. Yes, it's maximally 90 degrees. Yes, because otherwise it will shine to the ceiling. Okay, so how can I solve this problem? By the way, I tried to do some simulation, a very crude simulation here on GeoGebra. Let us check that. Of course, the numbers are different. So this is probably what I made. Okay. So this is, for example, assume that this here is my laser beam here. So this is my pen. And then I actually, this is the point light or light point, whatever you want to. So it's moving. So let's check that. So then I press here. So let us see what happens. So this is what I want. I'm rotating it, and then of course I hope that you agree that this will speed up. Do you agree? So let me just do it once more. So it was intuitively correct. Yes. So let me just make it 0. Okay. You see, this point is moving slow, and it is speeding up. So it's not a uniform motion. Yes. Is that clear? Something like this. I want to find the speed of this red dot. If I give you how fast I am rotating. Okay, something like this. Okay, so let us go back to the slides here. To the board. Okay, I want to hear from you. How do you solve the problem? I mean, where is the starting point? Together we can give energy to the problem so that it is solved, yes? So how should I start? Everything you think, you just tell me, I will do it here for you. Yes, Hussein?
Do we get any angles between it?
Okay, so tell me what to do.
Because I was thinking of
I was thinking that's a good idea. So I will take a particular at some time. So assume that my particle is here.
yes,
Then it means that my pen is pointing in that
yes.
direction.
Then you have the side that is constant of
1.
and the other one is length. You take tangent.
So if you don't, yeah, exactly. Let me take this one x. Okay.
Sticky, you take
You are telling me this angle. Let me take it theta.
yes. And then
Okay, just wait a little bit. When I want to calculate the speed of this moving point, what I am interested in? I am interested in the rate at which x is changing over time. So the question mark to this problem is dx dt. Yes? So what you did is completely correct. So you actually picked a typical point and then give them some names. For example, you decided to call this theta, and then you decide, for example, to give this x, and if that's an x-axis, that's a good symbol. But the point is, I want you to understand, the question is asking about dx dt. Is that understandable? Okay. And now I want to hear from you. I think you are on the correct path. So what should I do now? You said something about tangent or something.
yes, I was thinking of finding a relationship.
Exactly. This is a very good phrase. You want to find a relation between these quantities. Why? Because this quantity is related to omega. Is that right? Because you know that how fast theta is increasing will be affected by the size of this omega. So they are related. So if I can find a connection between x and theta, it means somehow I can find a connection between x and omega. Yes? So that's a good starting point. But how can I find a connection between x and theta? It's a very Math 2C problem, yes? It's tangent of theta because this is a right angle triangle. So tangent of theta is equal to what? Opposite side divided by h. Let us keep h for the time being. Okay, then what happens? X becomes h times tangent of theta. Okay, let us see what happens here. X is a function of theta. I see it in front of me. But theta itself is also a function of time. Yes? Yes, thank you very much. X is a function of time, x is a function of theta, theta is a function of time. Yes, because my passage of time is t. But I am interested in this one. So what should I write? The formula is what? Can you help me to write it down? I am interested in dx dt, but I have an intermediate variable. So what should I do? I should write dx over d theta multiplied by d theta over dt. Yes? Okay. So this is my question mark. I hope that you agree that I can calculate this more or less easily, but might be you have forgotten. I can help you. So what should I do from here? I have to calculate dx d theta. So x is a function of theta. I want to calculate its derivative. You need to remember the formula for the derivative of tangent. And this is the formula in the formula sheet. The derivative of tangent of x is what? 1 over cosine squared x. We did it before. Okay? So that's the formula. So this means that dx d theta is what? Is h times 1 over cosine 2 theta. So I put them here. H, if you don't mind, let me put h in the numerator, divided by cosine to the power of 2 theta. But can you tell me what can I write for d theta over dt in physics? What is the meaning of the rate at which the angle is changing over time? Yes? That's exactly the definition of the angular speed or angular velocity. Yes? So this is nothing except omega. Yes, that is omega. Is that clear? What is the meaning of this in mathematics? The rate at which this angle is changing over time. That's exactly the angular speed that you define in physics. Yes?
The only problem I had with this problem is the connection between t and theta. You see, x. You said x has a relationship with t with time. Doesn't theta also have it?
Yes, but I'm just trying to draw this picture because you remember when I was discussing about this, I draw some diagram like this to motivate you. So here, the quantity that I want is dx dt. Do you agree with this one? But the relation you found, t is not seen there.
So it's the same.
So you have to, yeah, exactly. Okay, so this becomes omega. So then what we can do here, we can finally answer the question. So dx so the question mark is equal to this quantity, which is omega times h divided by cosine squared theta. Yes? So let me clean this and write dx dt. That is the question. Of course, now I put the numerical values in. The numerical values, omega is given 1 radians per second, and this h is also given 1 meter. So then omega is 1, h is also 1. But then it means that dx dt is nothing except 1 over cosine to the power of 2 theta. But what does it mean? It means the speed that you are looking for is not constant. And in that simulation, you saw that it speeds up. Yes? So it means that if you want to answer this question, I have to give you extra piece of information at which time I want you to measure the speed. For example, I can say that what is the speed of this particle when theta is 45 degrees? What is the speed of the particle if theta is 15 degrees? Depending at which time I want to see at the speed, I have to give you an angle for that. Is that clear? Yes? Okay. But let me just, by the way, to see how it goes. Let us calculate this numerically for some values. So for example, let me take theta to be 45 degrees. At that moment of time, dx dt is what? Is 1 over cosine to the power of 245 degrees. But this is 1 over square root of 2, so it becomes 2. Yes? But what are the units? Meters per second. Why? Not centimeters, because the only length given in the problem was this height, and you wrote it in meters. So this is meters per second. So 2 meters per second. How many kilometers per hour? You have to multiply by 3.6. Yes, if you multiply by 3.6, it becomes 7.2 kilometers per hour. How fast you can walk normally? Approximately 6 kilometers per hour. So it's still a little bit faster than your walking speed, yes? But now, let us do some calculations. Let us calculate this when this is approximately 80 degrees. Okay, so let me calculate. Then I have to use my GeoGebra, okay, to see how it goes. I want to calculate how much is the speed when the angle reaches to 80 degrees. But I think it was far away from what we could see in GeoGebra, yes? So if I go to GeoGebra, still this is moving around, yes? But let me now to go to CAS view here, and I don't need this graphics, I don't need algebra here. So what should I want to, I want to calculate that quantity. So it is 1 over cosine. So let me put pair of brackets, and then I would write cosine, which angle I mentioned, 80. So I would write 80. If you remember to put the degree sign, I go here. And then, of course, I want to put power of 2. And then I want to find the approximate value. Yes. So 33.16. Yes, meters per second. So if you multiply that number by 33.16, and then you multiply it by which number, 3.6, it gives you 119 kilometers per hour. So when it reaches to this angle, then the speed of the moving particle is already 120 degrees, yes? 120 kilometers per hour. It is comparable to the speed of a cheetah, yes? I think cheetah can more or less run about this speed for 2 minutes or something, and if it cannot catch the prey, it will die actually, because he has used all its energy. Okay, but now let us see what happens if I increase the angle. For example, let us make it I cannot make it 90, that's clear. Yes, first of all, 90, they will not collide at all. On the other hand, cosine of 90 is how much? Is 0, so then 1 over 0 is not. But let me make it 89. So if you don't mind, let me go back here. Instead of doing it, let me write 89 here. And do this calculation once more. So now this is meters per second. And if you take that number and multiply it by 3.6, so 328, and then 3.14, and then I multiply it by 3.6, yes? This is meters per second, yes? So this is this number now. It's actually 11,000 something. So 12,000 kilometers per hour. So if I go up to there, if I have done the calculations right, yes? Yes?
How did you get the angular velocity earlier to be 1?
No, I told you that, I just mentioned that angular velocity of 1 radians per second is manageable by human, yes? Because 1 radians per second, it means that in 1 second, I rotate my laser pen 57 degrees. It's reasonable. Yes, but of course you can. The reason that I chose 1, because I don't want to mess up with the calculations. It will not change anything. So this speed is not that high, by the way. That was not my expectation. It should be much, much higher, isn't it? Yeah, there is a reason I'm talking about this. First of all, you know that how much is the speed of the shuttle, NASA shuttle? It's approximately 30,000 kilometers per hour. Okay? And how fast Earth is orbiting Sun? You should be able to calculate these numbers in your physics course. So it's good to have, it's approximately 30 kilometers per second. Okay? And how much is that? Kilometers per hour? 30 multiplied by 3,600. 108,000 kilometers per hour. So we have a quite adventure, yes, on the Earth, but we don't feel it. So anyway, this number, hypothetically, this number can be even larger than the speed of light. Why is that? Can you tell me? This is why I was expecting that at 89 we should have a very big number.
It's faster at 89.999.
My calculation is wrong here?
No, I mean it's faster than the speed of light at 89.999.
99, yes, because, by the way, could you realize that this can happen? This is speed. Why? Because, let us look at this function. I take the limit of this function when I send theta to 90 degrees. Yes? So it becomes 1. Cosine 90 is 0. I will not be able to put 0, of course, here, but I can approach to 90 as much as I want to. Then what happens? Cosine theta becomes negligible, and 1 over negligible is infinity. What does it mean? When I say this limit is infinity, it means that I can make this number bigger than any positive number that I want to. I can even make it bigger than 1 billion billion billion, so let alone the speed of light. So that's the difference between physics and mathematics, yes? So, but what happens in reality, by the way? Because then if I can move it more than the speed of light, might be there are some contradictions with Einstein's relativity theory that every speed should be below the speed of light. And then how can you talk about that? Yes, do you want to say something? No? Okay, think about this problem. By the way, this is important, by the way. One thing we didn't see about this, when I do that, this length is also increasing. And if this is really light beam, it takes time for light beam to travel that and you see the point light. It is not immediate. Do you understand that? When I change it, of course, it takes time that the photon of light goes from here to here. And when I actually increase this angle, this distance that the light is supposed to travel is also longer. Yes? By the way, let us calculate that distance. How do you calculate the distance? So how can I calculate the distance? Yes?
Well, we could use
The formula. So the distance is the Pythagoras theorem. Yes? So the distance, let me call it d. D is square root of this length to power 2, which is simple, but this length x to power 2. Yes? But then what is x? X is h tangent of theta. Yes? So this becomes square root of 1. But what is h in our problem? It is 1. So this just becomes tangent theta squared. And this is also a famous formula in chapter 2. Do you remember 1 plus tangent theta squared is 1 over cosine theta squared? And then this becomes 1 over cosine theta. So this means that the distance is also getting very big, but not as big as the speed, because a speed is related to the inverse of the second power, but the distance is the inverse of the first power of cosine. Okay? So how much time I need for the photon to reach from here to that distance? So what is that? Time is the speed of the photon, which is the speed of light. The distance divided by the speed of light, which is usually denoted by c in physics courses. Yes. So this means that this becomes 1 over c cosine theta. Yes. But look, even though you might think that this t is very, very small, is that right? Because c is the speed of light is so huge, you might think that, okay, 1 over that is negligible. Is that right? Yes or no?
No.
No, because in the competition between 1 over c and 1 over cosine theta, 1 over cosine theta will win eventually. Yes, because this is 1 over c times 1 over cosine theta. This is a constant, but a very small constant. 1 over 300,000 or something. Okay, that's a constant, very small constant. But what is the limit of 1 over cosine theta when theta goes to 90?
0.
No? Infinity. Yes? Because cosine of 90 is 0. So it means that when I get closer and closer to 90, this becomes so small so that when 1 over that small number is a huge quantity. And no one can win when it comes to competition with infinity, even the speed of light. Even though this is very, very small, but this is extremely huge. So at some point, this will start winning. And it means that you see this delay. Yes, the time that is needed that for this photon of light reaches to this point is quite clear. This is not instant. Is that clear? And that's already happening in sun, for example. It takes 8 minutes for the photon of light to travel from sun to the earth. Yes? So when you look at the sun, you see the sun not right now, you see the past of the sun 8 minutes before. That's one way you see that through telescopes. You are looking at the real pictures of the old universe. They are not, by the way, hypothetical. You are seeing the history of the universe, not how the stars are there at the right time. Yes, yeah, that's interesting. So I mean, these kinds of analysis, so that you learn actually quite a lot. So the notion of limit and everything that you learn, you can see this in practice. Okay? Okay, so that is actually what I wanted to discuss about. Any questions? Okay, so this chapter is completely finished. So let me pause recording here. Do you have any questions regarding the problem? Okay, so I will pause this.